not only physics but chemistry, and also is used widely in forensic science. And I'll explain how it's used, but I need to go into some theory first. So I want you to think about this period, why you think that happened. I'm not going to give you the answer right now, but I'm going to start going through the lesson, and then maybe you could suppose suggestions throughout. Do you know already why that happened?
I have a good guess.
You have a good guess? Okay. Take a guess. I'm curious.
So I think it's like the light that is used to like reflect from the material that you see is like blocked by the oil. So therefore there isn't a reflection, so you can't see anything that's like inside the oil.
Okay, good idea. Good idea. I'm not going to say yes or no yet. I don't want people to think still. You're on the right track of using obviously the light and what you see from the light for sure. And then we'll specifically talk about why that halo is there as well, as from looking in the side you don't see anything. Yeah.
Well, I had to look up the definition of refraction exactly.
Okay.
You look it up, and then you put it with this. It makes sense because it says the fact or phenomenon of light, radio waves, etc., being deflected and passing obliquely through the interface between one medium and another in varying intensity. So there you have two different sided beakers, I guess, and then I guess the light or something it refracts.
Yeah, but before I put the fluid in, it was fine, right?
Yeah.
But it's the fluid that caused it, so you have to make that connection. You're on the right track because you're right. That is the definition of refraction, and we'll talk about how it's to do with the bending of light. So you're on the right track for sure. That the light is being bent in a certain way, but it was only when I added the actual vegetable oil that it started.
Is it because the oil on the outside and also the shape of the container, maybe the light kind of goes around the inside one?
Not around, no. It's a good idea though. Again, you're thinking of the idea of cloaking with the fighter we talked about with the U.S. Strike, whatever the fighter jet is called, where it bends.
On the next slide, it shows the bending of a wave as it passes at an angle. So I thought maybe
It's going to bend, but it's not going to bend around it. That's the thing. Okay, you're right because you see the idea of bending. Good. That it will be bent in light, but the light itself. Hey, thank you for the beakers. The light. Thank you. The light itself will not actually bend around the container. Okay, we're going to talk about how this actually works and what you're seeing from above and from the side. The light, it's really going through it. And I'm going to leave that to you to think about so that by the end of the lesson today, you can figure out and understand why it happens. So we're going to talk about refraction, as you guys mentioned, and then we're going to use what's called Snell's law. Okay, Snell's law. So let's go. And it's easiest to explain with a diagram. And the diagram you're going to see is on the left and the right. You're going to see there's two different diagrams. One where an EM wave travels from air to glass, and then on the right where the EM wave travels from glass to air. Okay, from air to glass and then glass to air. Now, the idea of refraction has to do with the actual wave bending. Okay, when it bends from one medium to another. What might cause it to bend? What might cause it to bend? Yeah.
A mirror.
A mirror? Okay, so a mirror reflects light for sure, which I guess is considered bending. This is more, so Theo, I'm talking about this. Ready? Take a look. So the light comes through, and then it's bent. This is reflected. So yes, a mirrored surface.
A glass prism.
A prism could cause light to bend? Yeah, for sure. You've seen that. A prism shows all the colors of the spectrum. It absolutely bends light. It actually breaks light into all of its different wavelength segments. Katie? The material clearly, right? Because look, air is here and glass is here. So the bending of light is a function of the actual material itself. Very good. The material itself. Now, the reason we see light bending has to do with the actual waves slowing down or speeding up. Certain materials allow EM waves or light waves or waves in general right now. We'll just say, I'll say waves in general. Allow waves to either speed up or slow down if these media are transparent. Okay, these media have to be transparent. So the idea here is that this wave bends what we say toward the normal. Toward the normal. Now, theta I is the angle what we call of incidence. The angle of incidence. That's the angle that it comes to hit the actual surface with. And this is one of the few times where we measure the angle with respect to the normal. The normal is this right here, if you don't know what I'm talking about. This dashed line that you're seeing, the normal is like the y-axis. Theta is drawn with respect to the y-axis in this application, where in the past it's always been drawn with respect to the x-axis. we usually denote, and I'll point to it, we usually denote this as theta right here. And then after the wave comes through, we normally had been noting this as theta right here. Okay, it's just more of a acceptance in this field, in this area, that it's been used toward the normal. That's the reason I'm going to teach it that way. I know it seems like it's going to be more confusing, but it's not. Just remember that this is called the normal itself. And you'll see later why we don't use this angle. In section 15.2, we're going to see that when we get to some different phenomena that exist. So again, this happens, all that's happening is that light is being sped up or slowed down. Okay, light is being sped up or slowed down. If the light moves from material that has a speed that's higher to one that's lower, it bends toward the normal. So for example, in air, this visible light travels at a higher speed than it does in glass. So if you want to jot that down, you could say that the speed that it travels at in glass is lower than air. The wave is traveling at a higher speed, then it suddenly slows down when it hits glass, and it bends toward the normal. What would this ray look like if it didn't bend? Ready? Take a look. I'm going to draw it. You don't have to draw this, but you could just write this out. Or draw yourself at least a dashed line. This is what the ray would look like if it didn't bend. Take a look at that blue dashed line, right? This ray would pass right through and end up here. But what I'm saying is that because the wave slowed down, it bent toward the normal. Again, toward the normal when it slows down. And then what happens from glass to air? Instead of slowing down, what is it doing? Speeding up, right? Because if it slows down from air to glass, well, from glass to air, it's got to speed up. It's the opposite of the two things that are happening. And take a look. The angle that it came in at from glass and the angle that it exited at from air, now the angle exiting is bigger. It's the opposite of this previous one. Okay, so again, what we're saying here is that if light moves from material that's a higher speed to a lower speed, it's going to bend toward the normal. Toward the normal. What if the ray came in like this? What do you think will happen if the ray comes in like this? So again, watch the way I'm motioning. What if the ray actually came right along this vertical here?
Would it go in the same direction? Would it just go out in the same direction?
Yeah, it would pass right through. Okay, so all of this occurs when waves hit a boundary at an angle, other than 90 degrees, I guess we could say. Okay, again, this only occurs when the wave comes in at an angle. If it comes in at a 90-degree angle or perpendicular to the surface, then we're not going to get any sort of refraction. Okay, perpendicular to the surface, like that, the ray would pass directly through. It's when a ray comes in at an angle that it doesn't follow this path anymore, but it bends, what we say, toward the normal, if it is, again, slowing down. This is an example of slowing down. The one on the right is speeding up. Okay, and I'm looking from top to bottom. Top to bottom. That's why the arrows are drawn that way. Don't let the reflection throw you off. The reflection is what we saw the other day in section 14.2 and 14.4. We talked about reflection. We talked about diffuse and specular reflection. That's what the idea is here. Okay, this is just simple reflection. This is the refraction down here. All right, let's actually makes up the property that we're going to use, which is called an index of refraction. An index of refraction. And this slide might help you to hypothesize what's going on here. Okay? What's going on with the Pyrex and the vegetable oil. So first, the index of refraction is just a ratio. It's a ratio that involves what's called the speed of light, which we know as c, over the speed of light in that medium. In that medium. So what do we know? Well, we know that when EM waves travel through space, they go at the speed of light. But when they hit the atmosphere, what happens?
Slow down.
Yeah, they gotta slow down. And suddenly there's like interference. Think about like you're running, and then you start running through like a pool of water. When you run through water, you run like this, right? Like really slow. That's like what EM waves are doing. They're going through space, traveling at this high speed, not getting interrupted at all, the whole time. Having a great time, and then they hit Earth's atmosphere, and suddenly they have to slow or change speed. Now, we see a lot more than just that. We see the color blue in the sky because of the actual angle that the light is bent at when it enters and comes through the atmosphere. That's the blue we're seeing. We sometimes see red on a sunset. We sometimes see orange and purple and pink and all these beautiful colors. Where are they coming from? It has to do with the angle at which you're seeing those light rays, especially when the sun is like right on the horizon. Okay, the angle is changing. So in this case, we're looking at the speed in space. Well, the speed in space is as fast as it can be. It's as fast as it could possibly be. It's 3 times 10 to the 8. That's always true. So that's the numerator when you want to find out what's called the index of refraction of a material. It's always the numerator. Well, what could you tell me about the denominator? I'm not asking for the number. I'm asking for a general statement that you can use to relate it to the numerator. What could you tell me about the denominator when compared to the numerator? There is an answer that is correct. Think about it for a second. Theo?
It should always be bigger. Mostly.
Mostly. Emma?
It would be smaller,
Could you explain why, Emma?
because that once it's going through a different medium, that's when it slows down.
Yeah, remember, so Theo, you're on the right track that it has to be an extreme slow or faster, right? Now, if this is the speed of light in a vacuum, that's the fastest you can go.
Yeah, but I thought like for some reason it'd be opposite. It doesn't matter.
But you get the idea?
Yeah.
Okay, so the wave slows down. So this number is something less than c. It's some number less than c. I don't care what it is, but it's less than c. Take any fraction, please. Any fraction. Make the numerator bigger than the denominator. You can always conclude that the number is
Greater than 1.
thank you. n will always be greater than or equal to 1. It's a big thing we should jot down. You will never have an n value. Oh, it's not showing up on your screen. There it is. It's not showing up. It's not showing up. It's not the. It's not any value less than 1 simply because the numerator must always be greater than the denominator. Now, if it's an EM wave traveling through empty space in a vacuum, it's not going to bend at all. Okay, it's not going to bend at all. We're going to go through a table in a minute, and you should recognize that in air, we're going to say n is 1. In air, like regular air that we're in right now. But it does bend, and it does disperse when it goes through the atmosphere. Okay, let's make that clear. It definitely does slow down and change. But it's so minimal in air that the n value is like, I think it's like 1.0003. So we're going to use n equals 1 for air, really, even though it's not a vacuum. Is that clear? So let's jot that down, that n is going to be 1, even though it's... So we take a look at these values, and yeah, there's air. Look at the bottom right. 1.000293. Okay, so air is pretty much an n value of 1, meaning the speed of light really doesn't change much when it's traveling through our air as compared to empty space vacuum. Carbon dioxide is a little bit higher. The higher the number,
Faster? No, the slower it's going.
the more it slows down in that material. Let's jot that down. The higher the n value, right? The higher the n value means the smaller the denominator in the previous slide. The previous slide told us this. The previous slide told us that n equals c over v. Well, c is always the same number. So if n increases, what has to happen to v? How are they related? How are n and v related? How are n and v related? Inversely. So for n to go up, v has to go down. So the highest n values, for example, diamond, is the highest on this list. That has the slowest velocity for waves when it travels through its medium. Of the medium on the table here, sorry. I shouldn't say for all, right? Because there are other materials that are not listed here. But the slowest waves occur in diamond, meaning it slows down a whole lot. And we'll actually talk about why that makes diamond a specific thing. And by tomorrow, well, do I have you guys tomorrow? Yeah, day 1. By tomorrow, you'll know why you choose a diamond when you usually get like a ring. Why a diamond sparkles, the whole idea behind it. Okay, and we'll talk more about that tomorrow. But the idea has to do with its n value. And just recognize that diamond is the highest on the table. The fact that it's the highest helps it to sparkle. And we'll see how that works tomorrow. So these are all different n values for different material. Now look at cubic zirconia. What's cubic zirconia? Those that know what it is. Right here, I'll circle it. What is it physically?
It's like, it
Yeah, it's like the equivalent of like a knockoff diamond. It's not fake in the sense that like it doesn't actually exhibit the same properties, because it really does. That's why people get cubic zirconia. Cubic zirconia, I think it could be man-made actually too, but it's much more abundant on the earth than diamond is. The value of a material, or a ruby, or a gem, or a fine stone, usually is a function of its availability on the earth. So the less available something is, and the more applications it has, the more value it has. So although a diamond and cubic zirconia almost look the same in a ring, the reason people buy diamonds is nothing more than self-worth. It's sad, but it's the truth if you think about it. I know it really is, I don't want to be mean to say this, I know a lot of you probably wear diamonds. But when you think about it, what is that diamond ring doing for you? Anything? Does it serve any purpose?
Yes.
Honestly? Does it really though? Maybe if one day the world came to an end and you needed it for bargaining to trade for your life, fine, I'll let you go. But right now, in this day and age, besides giving you that esteem,
It establishes
that's what
sentimental purpose.
I was going to say. Well, first of all, anything that has sentimental purpose doesn't have to be a diamond.
True,
But I'm saying the value of a diamond, a lot of people feel like confidence if you're wearing something that has value to it, that has feeling, that air of confidence. But physically, what is diamond actually used for? Anyone know? I know you're going to
Cut other diamonds.
Not other, oh, yes, too, yes, but specifically.
Using certain microscopes.
It's using, I forget what I was going to say.
Frank was on the right line. He said cut other diamonds. Cut things in general. Saw blades that cut through things like granite. I watched an episode the other day of how it's made, and it was, I love that show. So, it's, oh yeah, it's on all the time. Curling, you know curling, the Olympic sport, you throw the stone and people go through the room. Amazing sport, by the way, for physics. Amazing, because it's all physics. But anyway, the granite rocks are actually pulled from only one country in the world. I forget what country, it was like somewhere in Europe. But the idea, we lost airplay. But the granite rocks themselves have to be cut in a certain way that the blade that's being used to cut it is diamond tipped, and they're spraying water the whole time to lower the amount of friction, so that the cut is nice and clean and smooth for the actual granite stone that they're going to use for the curling event. So diamond itself is very rare, but its usefulness as a tool is very, very, very useful. Gold, the same thing. Although gold people like to wear because it's very rare. Gold also has a very, very, very high electrical conductivity. Okay, it's used a lot with wiring, and like gold-plated wiring is used for signals to be better. Now, nowadays they're coming up with stuff that works even better than this. But for a long time, like you would use copper wires for the most part. But gold was a lot more efficient, had a lot more capacity, you could say. Better.
Isn't the whole point, right, of having like a diamond or having gold is one of the main reasons, especially gold, is because it's one of the few things that is, in this day and age, has some form of rarity on this earth.
Yeah, that was the first thing I said. Right, to do with the rarity on the earth, usually.
Right, so when you say that there's basically no value to it, the value is that...
No, I said there's no value when people wear it. It gives no value, really, if you think about it. It serves no purpose, is what I've been trying to get to.
If you don't wear diamonds, all those shielded slaves will have anything to do.
No, seriously, think about it. Wearing a diamond, what does that do? Like having the money in the bank versus wearing a diamond, in the end, it's the same thing.
Like if having money in the bank is theory. I mean, a lot of people, right, let's say you buy a $25 million diamond, right? That $25 million diamond in a lot of people's eyes is considered to be a lot more, they think it's a lot more stable, you know. If the economy ever defaults, they're able to go take it.
That was the stipulation I made in the beginning. I agree with you completely, but what I'm saying is purposefulness, right?
Right.
Purposefulness. You know, wearing a diamond ring serves no purpose besides getting that level of class. So what I was getting at, where I stemmed this whole conversation, was cubic zirconia exhibits a property that has a very close index of refraction, which is why people wear it, because that's the reason it actually sparkles that way. Okay, that's the reason it looks just like diamonds. It looks identical. Like people that don't know anything about jewels would have no idea if you walk down the street with a diamond versus cubic zirconia. No one is going to know that. It will literally trick anyone. If you're someone who's a gem expert or someone that works in a jewelry place and sits there with a little, what is that, a monocle, right? The little thing they look through? They can probably figure it out, obviously. But the idea here has to do with the index of refraction. That's going to lead us to this idea here with the vegetable oil. So let's take a look at Snell's law so we can really understand what's happening here with this. So, Snell's law allows us to have a way to solve for the angle at which the light is either refracted through or the incident angle that it came in at. based on the two materials themselves. So Ni is the index of refraction of the first material. Nr is the index of refraction of the refracted material or second material. So in a case where you're going from air to glass, right, if you're going, well, let's say water to glass, just for the sake of it. If I go from water to glass, and I have to draw the direction, that matters, and that's the incident ray coming in, well then water would go in for Ni, whatever the water value is, which I think is 1.3 repeating. It was in the table. Yeah, 1.3 repeating. So in this case, Ni is whatever water is. And then glass, where's regular glass? We'll just say crown glass, I guess, because you have crown or flint both on the table, right? Yeah. It is 1.52. Now, based on those two numbers, all you need besides that is an angle, one or the other. So if I know this is the normal, right? Draw yourself a normal, please. It's like that perpendicular line coming off. Hence normal force, right? Doesn't that look like the normal force, the line? That's how you can remember that that's the dashed line. It's the normal, like the normal force. It's not obviously a force though. The angle of incidence in this case, let's say, is 20 degrees. Well, the question becomes, are we going from a slower to a faster moving material? What's going to happen to the angle? Let's make believe we have no idea about the relationship of whether it should bend toward or away from the normal. And let's go ahead and prove it. So the angle that it comes out as is unknown. So we can tell that, the incoming angle is simply 20 degrees, and we're trying to figure out the angle that it comes out at, theta r. So we can go ahead and use Snell's law. Now, from your math class last year, and possibly if you've even gone into trig again already, I don't think you have yet in your junior class. Have you gone into trig yet or no? Yeah, but you did it as sophomores. You solve for the angle theta. How do you find the angle when you're doing stuff with sine and cosine? What kind of function do you have to use? Inverse, the inverse function. Remember like sine -1 or cosine -1? So your goal here is to find theta r. So to find theta r, you got to divide by nr up here first. It's a coefficient. It's just like a coefficient, the nr. Leaving behind sine theta r. Okay, again, divide by nr first. I'm at the bottom here in red.
Yeah.
Divide by nr. Then you want to get theta r by itself, so to get rid of sine, you have to do sine inverse of both sides. Now, you have to do sine inverse of this entire expression on the left-hand side. Sine inverse and sine do not cancel in that expression. So please be careful. So your answer looks like this in the end. How far up?
Yeah.
Got it? So if we're trying to solve for theta r, we have to take what's called the sine inverse of both sides. So take the sine inverse of both sides. That's what I have. I put it in blue so you can see. Put the sine inverse of both sides. Now on the right-hand side, the sine inverse of the sine of theta r is what you're doing on purpose to get theta r. The whole goal of this is to solve for theta r. So on the right-hand side, that is true. The sine inverse of sine is indeed just theta. So they don't really cancel, but it's like they're canceling. Okay, the inverse functions of each other. If I take f of inverse of x, it's just x always. It's a rule you're going to learn, or you've already learned in Algebra 1 as a 9th grader, or you're going to learn this year in Algebra 2, that if you take the inverse of a function, it goes back to the independent variable. So like f of inverse x is just x. So sine inverse of sine of x would just be x, or just in this case theta. So this is what theta equals in the end. Okay, this is simply theta r, and it's equal to this entire expression right here. Now, you could plug in numbers in the beginning. Plug in a number for ni, for nr, for theta I. All those could be plugged in at the very beginning of the problem, but you need to recognize that with sine and cosine and tangent, rounding is going to become a big issue. Because when you take the sign of a number, it's always a decimal. You want to keep at least 4 decimal spots when you're rounding in the middle of a problem with sine, cosine, tangent, the any trig function. You probably learned about that last year in math class, or Mr. Hall said you can either store it in the calculator, or you can just use the calculator and press second answer to call up the previous answer, and it'll use all the decimal spots. Okay, so my recommendation would be to solve it the way I did here, because this is very exact. You're going to plug in the three numbers for ni, theta I, and nr, and then you get the exact answer for theta r. If you plug in numbers in the beginning, just please keep at least 4 decimal spots. 4 for the sign portion of what you plug in. Okay, let's look at an example of this so we can see that. So a light wave traveling through air strikes a flat, smooth surface made of fused quartz at an angle of 25 degrees. Determine the angle of refraction. Determine the angle of refraction. So that's exactly what we're doing from the last example. We're solving for theta r. That's what this question is asking us. So if you want to, go back to the last example, that solution we had. It was this. The last solution told me that if I solve Snell's law, I'll get this always for theta r. You don't have to memorize this. You could solve it every time. Sine inverse of ni sine theta I all over nr. Okay, that's what theta r is going to be. Where does that come from? It comes from the last slide. I'm not going to resolve it. If you don't want to solve generically, you could have also have plugged in. Since we're going from, it looks like what, air? So ni is 1 for air. And it's going to fused quartz. Fused quartz is 1.458. This is on your table I'm reading it from. Okay, there's fused quartz right there. So it's going from air, ni equals 1, to fused quartz, and r equals 1.458. That's fused quartz. So this wave is going from a fast-moving medium to a slower-moving medium. It will bend toward the normal. Let's prove that. The angle that it comes in at is 25 degrees. If I'm drawing this, here's the normal. Here's the angle that it's coming in at. And remember, that angle is always drawn with respect to the normal. If I draw the normal on the other side also, I know already that this is going to bend toward the normal. I know that it's going to bend toward the normal because it's going from faster to slower, and we talked about that earlier in the class. So I could already draw my other ray like this. I'll leave the angle blank for now. I'll call it theta r. That's what we're looking for right there, theta r. I'm looking for that in red. But I know that theta r is going to be definitely less than 25. Because I'm going from faster to slower, it slows down, the wave bends toward the normal. That's going to become not just memorization, but understanding soon as well. So if we're solving for theta r, let's go ahead and plug in. You can plug in right up here. We take the sine inverse of 1 times sine 25 all over 1.458. Make sure you are in degree mode. That's a 1 times sine 25 all over 1.458. Please make sure you're in degree mode. If you're not, you don't know how to check, you hit mode and then check. I highly recommend that you do this if you have a calculator with you right now. I recommend it. I almost encourage it strongly. If you wanted to plug in the beginning in Snell's law directly, I'll put that at the bottom, the alternate way to do it. You could have plugged in the beginning. There's ni times sine theta I, which equals nr times sine theta r. Okay, you could plug it in the beginning and you'll have that at the bottom, and then you just have to solve for theta r. The same thing though, you're going to divide by 1.458. It's going to end up with what you have there in blue. You're going to take the sine inverse. You're going to get exactly what you have in blue. What do you get as a number? What do you get as a number for this one? When you plug this in. Theta r becomes, what do you got, Ellie?
I don't know if this is right, but 16.84.
So why did you say you don't know if it's right? I'm curious.
Because I feel like it looks too big. Oh, actually, no.
What was the one statement we made? It's going to be less than 25. So you should have been like, you know what, this is reasonable at least, right? If you had done something greater than 25, then you should definitely say, you know what, this is not right. Because I went from a fast-moving medium to a slow-moving medium, the angle should get smaller, right? It should get smaller. That's what we kind of went through at the beginning. And again, it's not necessarily going to be something you're going to memorize today. But as you go through more of these problems, you're going to see that When you go from faster to slower, it bends toward the normal. Toward the normal. Let's try one more of these. Go ahead and try it on your own. A light wave travels from air through an unknown material. So you know the first material is air, you don't know the second. If the angle it hits the medium at, with respect to the normal, is 30, and the refraction angle is 12, determine the material that it passes through. So go ahead and try to figure out what you know. Write down what you know. Write down what you're looking for. You might have to use your table to figure out the material. Okay? You might have to use that table that you had on the previous slide, a couple slides ago, to find out what is the material itself here. What is the unknown material? This is where, by the way, it comes out to be stuff like, or where you see this application in forensic science. To determine unknown material, they actually determine this. If you're struggling, take a look up to at least have your givens, see if your givens are correct. You're starting in air, so NI should be 1. Your angle that you hit the medium at is 30, that's theta I. The refracted angle is 12. And you're trying to find the material, which means you need NR. If you can find out the index of refraction of the second material, then you can find out what is that material by matching it up with the actual table value. So I can go ahead and solve for NR if I want to. Like I could solve algebraically here very easily, or I could plug in numbers if I'd like to. Again, it's up to you to decide. NR is being multiplied by sine theta r, so I'm going to divide by that on both sides. So this is the expression for NR right there. Plug in numbers. Make sure you don't try and cancel sine or something ridiculous like that. Sine is a function. Sine over sine does not really cancel if they're two different angles. Okay, one is theta I, one is theta r. So please do not try and cancel something like sine. You should have a 1 times sine 30 over sine 12, giving you... Katie? I thought your hand up. I thought your hand was up, sorry. What do you got? 2.4. Okay, we got NR equals 2.4. Again, plugging in 30 here in the numerator for theta I, 12 for theta R, 1 for NI. So what material is this one, according to the table? Diamond. Yeah, diamond was closest to 2.4. It's never going to be exactly what you want it to be, right? Now, I'm going to give you like a minute break or so for the next period. Before we go further though, think about this again. I know, it seems like still you might be a little bit confused, right? But think about what's happening inside of here right now. So if you're in a pool, and I'm outside the pool, you drop your ID card, something like this. If you're like inside of a, or your brother or sister's like in a backyard pool that's underground, or not underground, like in-ground pool, as opposed to above ground, and you're looking down at them, right? You're looking down at them from outside the pool. Sometimes you ever see the body is like staggered. Do you know what I'm saying right now?
Yeah.
Your body is literally shifted to the right or shifted to the left. Yeah, or you put a pencil in a glass of water, and you see the pencil looks like it's broken. It literally looks like the pencil goes in the water, and then you see the pencil continuing over here. What you're seeing is that boundary of refraction. You're seeing two materials, air and water. Air's refractive index is 1. Water's is 1.33. So you see the effect. So take that to this now.
Well, light's going from air to
Pyrex.
liquid, so
Or in the liquid first, good.
N must be like very low.
Yeah. Something to do with N for sure.
Is it it enters from air, the Pyrex, and the angle of refraction, like, oh, because there's a second Pyrex and also it goes around that.
So why am I not seeing it in a Pyrex? That was the question, though, guys. Why am I not seeing this? Let me think of another hint to give. If you took, this is crazy, but think about it, okay? Think about this for a second. If you took water, a glass of water, okay? Take a glass of water, literally. And you add more water to that water. And somehow the water that you add could somehow stay in the middle of the water. Would you see the other water you added as a separate entity from the water that was in there already?
No.
We would all look at the same thing, right?
Yeah.
Because water has the same properties no matter what, it's water, right? So how would you relate that to this? Katie?
Is it because glass and that oil have the same,
What's the term?
fraction
Yes.
and
Index.
value?
Yeah, and value. Oil, vegetable oil, turns out, has almost the exact same index of refraction as Pyrex does. It's one of the few things where you see two materials that are totally separate and different materials have almost the exact same index. So it's like as if you took oil. If I keep adding oil to oil, you don't see it, right? You don't see a difference in that oil. If I add Pyrex oil, you also don't see a difference. Because Pyrex and oil have the same exact N value. They're identical to one another. Okay, that's why you don't see anything actually happening. Now, the reason that you're seeing a little halo at the top is because although they're so close, they're not the exact same thing to like 25 decimal spots because they're not the same material physically. They may be close in indices of refraction, but they're not identical to every extent. So from above, you see a little halo. And actually, where that halo is located can tell you if the other material is a little bit above the N value or a little bit below the N value of the material it's submerged in. So in crime scenes, you know what they do? They take materials that they don't know, unknown fibers at crime scenes. So you have a fiber at a crime scene. You don't know if it's a piece of rayon, is it a piece of cotton, is it a piece of this, whatever polymer it's made of. They actually can test it in several samples of varying materials or liquids and see out of those liquids when does it pretty much either A, disappear, and you know the N value is around that value, or is the shadow outside or inside of the material? In a microscope you can see it really, the shadow. Is it outside or inside of the material? If it's outside or inside, it indicates whether you have to look for a higher N value or a lower N value to see what kind of material that you have. So it's used for that analysis so you can see what the material actually is. Okay, but again, it goes back to the idea of an index of refraction. If it's the same exact index, you literally don't see the other material itself. Right? Yeah. Okay, take like a 2-minute break.